There is a question that has quietly broken physics for almost 40 years. If a black hole eats too fast, it should starve itself. The very act of feeding should blast out enough energy to destroy its own food supply. And yet, at the center of nearly every massive galaxy in the universe, black holes have somehow kept growing for billions of years without ever running out of fuel. Nobody could explain how, until 3 weeks ago. A team of astronomers pointed the most powerful telescope ever built at a galaxy 145 million light-years away, and for the first time in the history of astronomy, they watched a supermassive black hole quietly feeding itself in real time. What they found rewrites how we understand the engines at the center of galaxies. And it happened so recently that most of the world doesn't know about it yet. By the end of this video, you'll understand exactly how an object powerful enough to destroy entire star systems has been secretly keeping itself alive this entire time. Let's start with the paradox itself, because without it, none of this makes sense. A supermassive black hole isn't a vacuum cleaner. It doesn't simply pull matter toward it and swallow everything nearby. Feeding a black hole is closer to threading a needle at galactic scale. Gas has to fall inward from thousands of light-years away, lose almost all of its spin, and land in exactly the right place to be consumed. And here's where the paradox begins. As gas falls toward a feeding black hole, it heats up violently, and that black hole fires out jets of energy so powerful they can blow gas clean out of a galaxy. Picture trying to feed a fire while the fire itself keeps blasting your fuel supply away before it reaches the flame. For decades, that was the unsolved problem sitting at the heart of astrophysics. If black holes are this destructive to their own food source, how do they keep growing for billions of years? Astronomers had a theory, but no proof. They suspected that some of the energy blasted outward by a feeding black hole doesn't simply vanish into deep space. They suspected it might loop back, cool down, and fall inward again, feeding the very same black hole that created it in the first place. A self-sustaining loop. A cosmic recycling system. But a theory is not evidence, and for decades nobody had the tools to actually watch it happen. To understand why this was so hard to prove, you have to understand what a black hole actually needs in order to grow. It's not enough for gas to simply exist nearby. That gas has to lose almost all of its orbital motion, drift inward across thousands of light years, and somehow avoid getting blown away by the very radiation and jets the black hole produces while it eats. Imagine trying to walk toward a bonfire while someone stands next to it swinging a leaf blower directly at your face the entire time. That's roughly the scale of the problem astronomers were trying to explain. Every model built to describe this process ran into the same wall. The math suggested black holes should choke themselves out within a few million years, a blink of an eye on a cosmic timescale. But observations of the real universe showed black holes billions of years old, still growing, still active, still very much alive. That changed in a galaxy called NGC 4696, sitting at the heart of the Centaurus Cluster, one of the most massive collections of galaxies in our cosmic neighborhood. Older images from the Hubble Space Telescope had already picked up something strange near its center, a faint S-shaped swirl of glowing gas curling around the galaxy's core like smoke caught in a draft. Astronomers had seen this shape for years. What they couldn't tell was what it was actually doing. Was that gas falling inward? Was it drifting outward? Was it even moving at all? Or just sitting there, frozen in a snapshot? Hubble could show the shape. It could not show the motion. For years, that swirl sat in astronomy archives as an interesting but unsolved curiosity, a pretty picture with no clear physical story attached to it. Telescopes can only tell you what they're built to measure, and Hubble, remarkable as it is, simply wasn't designed to read motion out of faint infrared light with this level of precision. The shape stayed a mystery, filed away, waiting for an instrument sensitive enough to actually interrogate it properly. This is where the story turns, because motion is exactly what changes everything. An international team, led by researchers from the Université de Montréal, pointed the James Webb Space Telescope directly at that swirl. Webb carries an instrument called NIRSpec, and unlike a normal camera, it doesn't just capture light, it reads it. Every atom in that gas cloud, as it moves, stretches or compresses the exact wavelength of light it emits, the same way a siren sounds higher pitched as it races toward you and lower as it speeds away. By reading those tiny shifts in wavelength, precisely tracking a specific signal called the Passion Alpha line, the team could finally measure something Hubble never could. Not just where the gas was, where it was going, and how fast. This is a fundamentally different way of looking at the universe. A regular photograph freezes a single moment, a single frozen slice of light. What NIRSpec produces is closer to a velocity map, an image where every single point carries its own speed and direction embedded inside the color of the light itself. It's the difference between a photograph of a river and a device that tells you, for every square inch of that river, exactly how fast the water is moving and which way it's headed. Applied to a swirl of gas at the center of a galaxy 145 million light-years away, that kind of precision had simply never existed before. And what they found was almost too clean to be believed. The swirl wasn't static. It was a rotating disk of gas, roughly 800 light-years across, spinning around the black hole at speeds up to 600 kilometers every second. To put that in perspective, that's over 1,300,000 miles per hour, fast enough to cross the distance from New York to Los Angeles in about 7 seconds. An entire disk of superheated gas, larger than most star clusters, orbiting a single point in space at a speed that barely gives the mind time to process it. Stop and picture the scale of that disk for a second. 800 light-years wide is nearly 200 times the distance between our Sun and the nearest star system beyond our own. And every part of that entire structure is caught in a single coordinated spin, orbiting a point of gravity so extreme that light itself cannot escape from its center. This isn't chaos. It isn't scattered gas drifting randomly in every direction. It's an organized, disc-shaped structure, held together and shaped entirely by the gravity of the object at its center. But the rotating disk alone wasn't the discovery. It was what the team found feeding into it. Connected to that spinning disk, the researchers identified a massive filament of gas, a long thread-like structure stretching inward from farther out in the galaxy, funneling material directly toward the black hole's doorstep. Not scattered gas drifting randomly, a structured, organized channel, actively delivering fuel to the disk like a river feeding into a whirlpool. This was the first time astronomers had ever captured this kind of feeding structure in this much detail, at this scale, in real time. Here's the part that answers the original paradox. The team traced the filament's origin, and it didn't come from some distant, untouched reservoir of fresh gas. It came from material the black hole itself had already blasted outward, earlier in its feeding cycle. Jets fired from the black hole had pushed hot gas out into the galaxy's surrounding atmosphere, inflating enormous bubbles in the process. Around the edges of those bubbles, the gas began to cool. As it cooled, it became unstable, and magnetic fields threaded through the galaxy stretched that cooling gas into long, narrow filaments. Those filaments then fell back inward, feeding the very disk that feeds the black hole. Break that cycle down into its individual stages, because each one on its own is remarkable. First, the black hole feeds, and in doing so, fires out a jet of energy so powerful it can travel thousands of light years. Second, that jet slams into the surrounding gas and inflates a bubble, hollowing out a cavity in the galaxy's hot atmosphere, the same way a hot air balloon pushes outward against the air around it. Third, at the edges of that bubble, where the pushed-out gas meets the colder gas further out, the temperature drops sharply and the gas becomes thermally unstable, meaning it can no longer hold its shape as a smooth cloud. Fourth, magnetic fields woven through the galaxy, invisible but very real, grab hold of that unstable gas and stretch it into long, thin filaments, the way wind can pull smoke into ribbons. Fifth, gravity takes over, and those filaments fall back down toward the black hole, delivering fresh fuel to the rotating disk. And then the entire cycle begins again. Say that sequence slowly, because it matters. The black hole fires out energy. That energy pushes gas outward. The gas cools. Magnetic fields shape it into filaments. Gravity pulls those filaments back down, and the black hole eats its own exhaust. Not metaphorically, physically. A supermassive black hole, recycling its own waste product into its next meal, on a loop that can repeat for billions of years. One of the researchers on the team, Megan Donahue, a physics professor at Michigan State University, described the sheer volume of information Webb delivered in blunt terms. She said the observations were offering thousands of new facts and measurements, and admitted it was a lot to absorb. That's not the kind of thing a scientist says about a minor result. That's the kind of thing a scientist says when a single observation answers a question the field has been chasing for decades. Think about what this actually solves. For nearly 40 years, astronomers watched supermassive black holes sit at the center of galaxy after galaxy, growing steadily larger over cosmic time, without a clear mechanism explaining how they avoided starving themselves. Every model showed the same contradiction. The very process of feeding should choke off the fuel supply, and yet the black holes kept growing anyway. NGC 4696 didn't just add one more data point. It showed the actual physical mechanism in motion, gas rising, cooling, falling, and returning, an engine quietly running inside almost every massive galaxy in the universe, including, almost certainly, our own. If you're starting to see how strange and elegant this is, you're exactly the kind of person this channel is built for. We break down real peer-reviewed discoveries like this one, without exaggeration, without guesswork, just the actual science, explained clearly. Now here's where the story widens, because NGC 4696 isn't some cosmic outlier. Nearly every large galaxy in the universe has a supermassive black hole sitting at its center, and many of them show the same telltale sign: hot, X-ray glowing atmospheres surrounding their cores, the exact kind of environment where this recycling process could take place. Scientists have long suspected that similar feeding loops might explain how black holes across the universe sustain themselves without simply burning through all their fuel in a few million years. NGC 4696 is the first place anyone has actually watched the mechanism directly: gas motion measured, filament traced, disk mapped, cause and effect connected in a single coherent picture. That includes our own galaxy. At the center of the Milky Way sits Sagittarius, a star, a supermassive black hole roughly 4 million times the mass of our Sun. It's far quieter than the black hole in NGC 4696 right now, not actively feeding at nearly the same rate, but it sits in a similar kind of hot gas-rich environment. If this recycling mechanism really is common across galaxies with the right conditions, then somewhere in the slow, patient history of the Milky Way, our own black hole has likely gone through cycles like this too, firing out jets, cooling gas into filaments, pulling that material back in over and over, long before humans existed to witness any of it, and potentially again in the distant future. Astronomers now want to know how common this exact mechanism is. Is NGC 4696 a perfect, unusually clean example of something that happens everywhere, but is normally too faint or too tangled to observe clearly? Or is it a special case, shaped by the particular environment of the Centaurus Cluster? Follow-up observations are already being planned, pointing Webb's NIRSpec instrument at other galaxies with similar hot, X-ray bright cores, searching for the same signature, rotating disks fed by cooling filaments, to see whether this cosmic recycling loop is the rule or the exception. There's also a bigger consequence hiding inside this discovery, one that reaches far beyond a single black hole. These feeding cycles don't just sustain the black hole, they shape the galaxy around it. Every time a black hole fires off a jet, it injects energy into the surrounding gas, heating it, stirring it, sometimes even slowing down the formation of new stars across the entire galaxy. Astronomers call this process feedback, and it's considered one of the most important forces governing how galaxies grow, or stop growing, over billions of years. If black holes really do recycle their own exhaust into fuel, then this feedback loop isn't a one-time event. It's a continuous engine, quietly regulating an entire galaxy's evolution from the inside out, one bubble, one filament, one orbit at a time. This is where the discovery stops being about one black hole in one distant galaxy and starts being about something closer to a universal rule. If a black hole's own waste becomes its next meal, then the black hole isn't just a passive object sitting at the center of a galaxy, quietly growing while everything else happens around it. It's an active participant in the galaxy's entire life story, regulating star formation, shaping the surrounding gas, and sustaining itself through a loop it essentially built for itself. Galaxies without this kind of feeding cycle may evolve completely differently, growing more stars, staying colder, developing in ways that look nothing like a galaxy with an active recycling black hole at its heart. To see if the physics actually held up, modeling how gas would behave if it really was falling inward through a filament exactly like, the team tested their observations against a computer simulation of the one they found. The simulated gas took on a shape strikingly similar to what Webb had captured in NGC 4696. Real data and theoretical prediction lining up almost perfectly. That kind of agreement between observation and simulation is exactly what separates a strong hypothesis from a confirmed physical mechanism. Scientists are still cautious, still working through exactly how universal this process is across different types of galaxies, but the pieces now fit together in a way they simply didn't before. It's worth pausing here on what it actually takes to confirm something like this. Astronomers didn't just look at one pretty image and declare a mystery solved. They measured real velocities, traced a real filament back to its source, and then built an independent simulation to check whether the physics they proposed could actually produce what they observed. 3 separate lines of evidence, pointing toward the same conclusion. That's the difference between an educated guess and a genuine scientific breakthrough, and it's exactly why this result was accepted into a peer-reviewed journal, rather than staying a speculative theory on a whiteboard. If you strip away the technical language for a moment, here's what actually happened. For decades, black holes looked like they were breaking their own rules, feeding endlessly while appearing to destroy their food supply in the process. Now, for the first time, astronomers watched the missing piece fall into place. The waste isn't wasted, it's the next meal. One researcher summed up the entire discovery in a single sentence, calling black holes the universe's ultimate cosmic recyclers. Not destroyers, not simply consumers. Recyclers, running a self-sustaining loop that may explain how these objects have grown to billions of times the mass of our sun without ever running dry. That single phrase, cosmic recycler, does a lot of work because it completely inverts the image most people carry around in their heads. The popular idea of a black hole is something purely destructive, an object defined entirely by what it consumes and never gives back. What NGC 4696 suggests is closer to an ecosystem than a void. Energy goes out. Matter cools. Matter comes back in. Nothing about that process is chaotic or wasteful. It's closer to the water cycle on Earth: evaporation, condensation, rainfall, repeating endlessly, except instead of water moving between ocean and sky, it's superheated gas moving between a black hole's jets and its own gravitational pull on a scale that spans hundreds of light years and unfolds over millions of years at a time. And this brings us back to where we started, because this isn't just a story about one galaxy 145 million light-years away. It's a story about the machinery sitting at the center of nearly every large galaxy in the observable universe, including our own Milky Way. Every one of them may be running some version of this same quiet, patient cycle, invisible until a telescope powerful enough finally learned how to read the motion hidden inside the light. There's something worth sitting with here, beyond the physics. For 40 years, this cycle was running, completely unseen, in galaxy after galaxy across the universe, including possibly our own. Gas rising, cooling, falling, feeding, over and over for billions of years, with no observer anywhere to witness it. It didn't need us to happen. It didn't wait for us to build the right instrument. It simply continued, silently, the way it always had, until one summer, a team of astronomers finally built something sensitive enough to catch it in the act. That gap, between something being true and something being known, is where almost all of scientific discovery actually lives. The universe wasn't hiding this from us. We simply hadn't learned how to listen yet. What surprised you most about this discovery? The fact that black holes recycle their own fuel, or the fact that it took nearly 40 years to actually see it happen? I'd genuinely love to read your thoughts in the comments, and I do my best to reply to as many as I can. If you want more real, verified space discoveries explained clearly, without exaggeration, and without guesswork, subscribe and turn on notifications, because the universe keeps finding new ways to surprise the people paying attention.